Before the transformer, sequence tasks like translation relied on recurrent neural networks, or RNNs. RNNs process tokens sequentially, meaning the model must wait for word 3 to finish before processing word 4. This creates an inescapable computational bottleneck, preventing parallel processing during training. Additionally, as sentences grow longer, gradients vanish, making it extremely difficult to remember early words. In June 2017, researchers from Google published a groundbreaking paper, "Attention is All You Need." They proposed the transformer, an architecture that completely discarded recurrent loops. Instead of sequential processing, the transformer processes all words in a sequence at the exact same time. This unlocked massive, allowing models to train on unprecedented amounts of data in a fraction of the time. At a high level, the original transformer uses an encoder-decoder structure. The encoder takes the input sequence and translates it into a continuous stack of representations. The decoder then takes these representations and generates the output sequence, one word at a time. Both the encoder and decoder consist of multiple identical layers stacked on top of each other. Let's zoom into a single block of the encoder stack. First, words are converted into dense vectors called input embeddings. These embeddings are joined by positional encodings to preserve word order, then passed into multi-head attention. After attention, the output passes through a position-wise feed-forward network. Residual connections and normalization are applied around both sublayers to stabilize gradient flow. At the absolute core of the transformer is scaled dot product attention. For every word, the model computes 3 distinct vectors: a query, a key, and a value. The query represents the search term, the key acts as the indexing label, and the value holds the actual content. By matching queries against keys, the model decides how much attention to pay to each value. To calculate attention mathematically, we first multiply the query matrix Q by the transposed key matrix K. We scale this result by dividing by the square root of the key dimension, preventing extremely large dot products. A function is then applied to obtain normalized attention weights between 0 and 1. Finally, we multiply these weights by the value matrix V to produce the final attended representations. Instead of performing attention once, the transformer uses multi-head attention. The queries, keys, and values are projected into multiple lower-dimensional subspaces. This allows different heads to simultaneously learn different types of relationships between words. For example, one head might link pronouns to their nouns, while another head focuses on verbs and objects. Because transformers process all words at once, they have no built-in sense of order or position. To solve this, the authors introduced positional encodings, which are added directly to the input embeddings. They use sine and cosine functions of different frequencies to generate unique positional signatures. This mathematical trick allows the model to easily learn relative positions and scale to longer sequences. Now let's explore the decoder, which generates the output sequence. It contains 2 attention layers instead of 1: masked self-attention and encoder-decoder attention. Masked self-attention prevents the decoder from looking at future words during training, ensuring causality. The second layer, encoder-decoder attention, focuses on the encoder's output representations to extract the input meaning. There is a massive difference in how the transformer works during training versus inference. During training, we use teacher forcing, feeding the entire target sentence into the decoder at once with masking. This allows parallel training across the entire target text, saving massive computation. During inference, however, generation is autoregressive. We predict one word, feed it back, and predict the next. The transformer achieved state-of-the-art results on translation tasks almost immediately. On the WMT 2014 English to German task, it scored 28.4 BLEU points. More importantly, it achieved these results at a fraction of the training cost of prior architectures. It was over 10 times faster to train than previous sequence-to-sequence state-of-the-art models. The transformer architecture changed the field of artificial intelligence forever. By proving that self-attention is indeed all you need, it laid the foundation for modern foundational models. Large language models like GPT, Claude, BERT, and LLMA are all direct descendants of this design. From natural language to vision and biology, the transformer remains the gold standard of modern AI.